In this video, we are going to be looking at the some points of emphasis about proteins, right? So if we play this video, we can see that it starts off with the concept that again, a protein is a chain of amino acids, and we have kind of discussed this already in the third quarter. This time, we will emphasize the structure of the amino acid. So this is the first point of emphasis, which is the structure of of an amino acid. And again, it's a central carbon, right? And then the right side or the left side, whatever, has the carboxyl group, and then the other side has that amino group. And then a carboxyl group again is just a C double bond O, single bond to an OH, while an amino acid is an N connected to two H's. And again, you have that central carbon, and then you have an R, the variable group, and then this H is a filler just because carbon always has 4 bonds. So we do carbon counting also here. So again, if I am going to construct that on my own, I would have a central carbon, a carboxyl on one group, on one side, and then an amino group on the other side. That's it. And then an R. But again, if I do that, this carbon has 4 bonds. This carbon has only 3 bonds. So there must be one filler thing there. And again, this is important. As I mentioned, it's not presented in the video, unfortunately, but that's why this is the second point of emphasis. The second point of emphasis is once you have that amino acid, right? What makes an amino acid glycine? What makes it an alanine? What makes it a tryptophan and all the other amino acids, which you have 20 of them, is this R, right? So if you have this as just an H, if the R is just H, then the amino acid is glycine, right? If the R is CH3, right, then the amino acid is, if I remember it right, alanine. So this R here gives identity to your amino acid, okay? So that's why you have 20 amino acids. Why are they called all amino acids? Because they have the same structure. It's just that their R is different. If it's an H, again, it's a simple glycine amino acid. If it's CH3, it is alanine, and you could have even more complicated R's, or this R is called the side chain. Okay, so that's the second point of emphasis. So if we move through the video, again, this is the R group, and that is kind of important. And then you bond together amino acids, and this is the third point of emphasis, which is the type of bond that is created between amino acids to the next amino acid. This is the C to the N bond, and we call that a peptide bond. Okay, that's why when you have a chain of amino acids, we call it a polypeptide bond. Okay, because of that peptide bond. And then it was not emphasized here, but it's not emphasized in the video. Into my fourth point, and that fourth point is that every time you have an amino acid, again, central carbon, carboxyl group here, and then amino group on the other side, and then again you have an R, and then let's just say that this is glycine, so this is simple H, and then the second amino acid, again you have this central carbon, the amino group here, the carboxyl group on the other side, and this time let's make this alanine, so alanine is CH3, right? Again, to bond this and that, you have to create a carbon to nitrogen bond, but carbon already has 4 bonds, so it has to let go of the OH to make this bond available to connect to nitrogen. The same is true with nitrogen. Nitrogen has to let go of the H. So as a result, this O and OH gets removed, right? And that itself becomes water. when they are removed, then obviously now carbon has only 3 bonds. Now, and carbon needs 4 bonds, right? And then nitrogen here only has 3 bonds. See, one towards carbon and one towards hydrogen. And nitrogen needs 3 bonds. So that's why this fourth bond can be created. Okay? So that's the fifth point of emphasis for proteins, that you have to give up the OH of this side and the H of this side to kind of create water. Now, the next point of emphasis is this idea that proteins are more complicated than what we have discussed in the third quarter, and that is because they undergo through several levels of structure. The primary structure is just the string of amino acids. So, which amino acid is first, which is connected to the second, which is connected to the third. And in the third quarter, we discussed this as the sequence of amino acids. Remember, the tRNA brings amino acids to the ribosome, and then the ribosome severs the connection of that amino acid head from the tRNA and connects it to the second amino acid of the next tRNA that comes in. The order of the amino acid is just the primary structure. The secondary structure are these helices and beta sheets. And again, the idea for that is if you have a chain of amino acids, right? What comes in play here is now the side, the R. Remember, you have the central carbon, you have you have the carboxyl group on one side, you have the amino group on the other side, you have this filler H, and then you have this R. Because this R is variable, there are 20 different R's. And the thing with that is, when you have 20 different R's, some of them are polar, some of them are non-polar. Some of the polar stuff are positively charged, some of them are negatively charged, some are zero but still polar, some most of the non-polar have no charge, so neutral. So they have these 5 different properties. This R could be polar, could be non-polar, could be positively charged, could be negatively charged, it could be neutral, right? It could be neutral but still polar, it could be neutral but non-polar. So what does that have to do with the secondary structure? So again, you have this string, and the idea is, if this let me go back to the video where we can show the R in a chain there. You see, you have a chain, but all of the R's are on one side, right? So what happens is, what if this green R is positively charged, and then this blue R here over here is negatively charged? So what happens is, this positive and negative will attract, right? And most often will do like this. For example, this is the point here where the R is positive, and lower along the chain you have an R that is negative. Guess what? This positive will attract with the negative, right? And in some cases it will do like this. See what happens? And what if along the line there's another negative charge? So now it gets attracted again. And as you notice, you now form this helix, right? So that is not to say that the primary structure doesn't have anything to do with the secondary structure. It does, because remember, the reason why the chain of amino acids kind of connect and do like that is because of the R, right? And the R is obviously dictated by the sequence of which amino acid is first and which amino acid is second and first. So secondary structure is not completely independent of the primary structure. The secondary structure is just an effect of the interactions of the R of the primary structure, right? That's the first case. And then the second case could be that instead of this forming helices like this, a helix, I'm not sure if it's clear in the in your video that it's a helix, it could be a separate thing where this one, it's positive, right? It's connected with the negative, it's like that, and then connect this one is connected to the positive like this, and instead of a helix, you form like a flat sheet. See, you have a flat side. And why would it become flat? Again, think of it as this and that gets attracted, right? So you form a loop. But what if, as you form that, this and that repels? So if it repels, it will they will move away from each other like that. And instead of now having a helix, you now have a flat side. So what we call a beta sheet. Obviously, I am simplifying my explanations for you, right? When you take up advanced biochemistry, you would understand why, even better, why in the secondary structure you form helices or flat sheets. But the idea is you have helices and flat sheets. Then the third one is the tertiary structure, and then the tertiary structure is just the let's say the overall effect of having the secondary structure. So the addition, if you add all the if you add all the primary secondary structures, you have the tertiary structure. So what I mean by that is you might have in this part a helix part, and then here you might have a flat beta sheet part, and then helix again, and then flat sheet again, and then helix but to that direction, then helix to this direction, then helix to that direction, then flat sheet to this direction, flat sheet to that direction. So the shape of the protein becomes complicated, because remember, a protein is not just 2, 3, 4, 5 amino acids. It's thousands and hundreds and thousands of amino acids chained together. So if you add all the secondary structure here, helix here, flat sheet here, together, that makes up the first half of the structure of the amino acid. And the second half, and again, is because of the polar and the non-polar parts of the side chains. So, for example, if we think of this as this complicated shape of this t-shirt as the kind of the shape of the protein, again, another thing that makes this more complex is the water hating and water loving part. So if this part here is polar, it loves water, guess what? It will, and remember, proteins are in the nucleus, in the cell, which is, surrounded by water, cytoplasm. So this one would pop out because it loves water. If this part doesn't love water, guess what? It will fold in and kind of hide inside the protein. So what is already complicated because of the secondary helices and beta sheets gets more complicated by the parts of the protein folding in and parts of the protein folding out, because some R's are polar and some R's are non-polar, right? So that's the secondary structure of the protein. I mean, the tertiary structure of the protein. So again, the tertiary structure is because of all the secondary structure added, plus polar molecules popping, polar side chains popping out, and the non-polar side chains hiding from the water, meaning hiding inside the protein. At this point, you can call this a protein already. When it is already when it has a tertiary structure, it has a 3D shape, right? Because that is a three-dimensional shape. That's why I opt to illustrate it to you with a T-shirt, because this shape is a lot complicated. So that's a protein. Now, some proteins combine together and form um, protein complexes, right? So if we fast forward here, this one, this protein has different parts. It has the pink part, which is protein 1, the white part, which is protein 2, and the green part, which is protein 3. So a lot of times, different proteins created from different protein synthesis processes actually combine and work together to do the same function. So that is what we call the quaternary structure of proteins. But as long as you reach the tertiary structure, technically speaking, that is already a protein. When you have the primary structure, you can call it a polypeptide chain, not yet a protein. So I kind of gave you uh, I did not explain that in the third quarter because you did not need to know that. But now we are looking at a deeper zoom, and we are claiming that when you chain amino acids together, technically speaking, it's not yet a polypeptide unless it develops secondary structures, tertiary structures that then secondary structures like sheets and helices, which when added up plus the fact that some parts fold in and some parts fold out, you create tertiary structures. That's when you can technically call it a protein. But again, some proteins go even higher than that and merge with other proteins to do other functions, and that's what we call a quaternary structure of proteins. Okay, so those are the points of emphasis for that video, which is about proteins.